Hello, hello, beautiful people. Welcome to 11.4. Our SWABAT is to add and subtract rational expressions. Your warm-up for today is to find the sum or difference. So if you have not done so already, go ahead and press pause and complete this warm-up on your own. It's going to be really important that you can do this without me. Thank you. Press pause. So if you take one moment, just compare your work with my work. Main thing here is making sure that you can get your common denominator before we can add or subtract. We have to make sure that we have our common denominator before we can add or subtract. So for number 1, you should have gotten 1 over 15, and for number 2, 5 over 9. Okay, so let's go through some examples. Our first one is to find the sum or difference. Part A, 2n plus 3 over n squared minus 9 minus n over n squared minus 9. So what I like about this one in comparison to your warm-up is we already have a common denominator. It's right here. It's n squared minus 9. What I'm going to do then is just to combine the tops, the numerators, noticing this minus sign here. So it's really like we're adding the opposite. I want to make sure that I can count this as a negative sign. So I have 2n minus n, or 2n plus a negative n. That gives me n, and then plus 3. Delightful. Almost. Next thing I want to do is factor anything that can be factored. This, I'm looking at it, can't be factored. It's just n plus 3. It's delightful, just the way that it is. The denominator, however, is a special pattern. Let me remind you, a squared minus b squared is equal to a plus b times a minus b. I know you've seen this a million times, and I know that I've warned you that it keeps coming up. I don't have to use a box for this because I'm fully aware of this special pattern. Perfect square minus perfect square, delightful. It breaks to a plus b times a minus b. So in this case, the n squared will break down to n times n. And then what squared gives me 9? 3 and 3. Noticing that you have to have one positive and one negative. Well, what a coinkydink. I'm looking at the numerator and the denominators. They both have n plus 3 in common. So all I have left in the denominator is n minus 3. What would I have in the numerator? Just 1. And there you go. Let's try another one, just like the other one. So again, common denominator. It's a beautiful thing when they give it to us. Bless God for it. M plus 4. It's a funky little m there. And then what am I going to do? I'm going to add the numerators. 5 plus 7. 5 plus 7 is 12. Can I factor this at all? No, Miss Fitzgerald, that's crazy talk. So that's my final answer. So again, when we have a common denominator, it makes our lives about a million times easier. But we will not struggle to find one when we need to. For number 2, my directions are just to find the LCD. You really want to be careful when you're doing your classwork or your book assignment, because there are going to be problems where they just say to find the LCD. That means they don't want you to add, they don't want you to subtract, they just want to know what it is. So I'm kind of low-key ignoring that, and I'm only looking at the denominators, and I want to look at the numbers first. I'm looking at 28 and 7. What's the common denominator, or least common multiple of 28 and 7? Some people will automatically say, oh, 7. Because they think, oh, 7 goes into 7 and 7 goes into 28. That's not the question, though. The number has to fit into both of them. So instead of dividing these both by 7, I want to say that they both can go into 28. 28 goes into 28 one time, and 7 goes into 28 as well. It has to be big enough for both of these numbers to fit into it. And then you're looking at the k's. Well, they both already have some k's in common. I want them to be the same, except this one has a 2 and this one has a 3. Which one would be big enough for them to both fit into? Kind of like with the numbers, k squared can fit into k squared, but k cubed cannot fit into k squared. So I'm always going to go with the higher exponent, because it's big enough to fit itself and the little one as well. So that's my common denominator. That's all they want from us for that one. Looking at part B, they don't really seem to have anything in common. Ooh, went a little too far there. Because this is an x plus 5. Again, remember, we are ignoring that for these ones. And then this is a 9. So I'm going to say the common denominator is the 9 has to be represented, and I need an x plus 5. X plus 5 can go into itself, so I want to make sure that's covered. 9 can't go into there. They have absolutely nothing in common because we don't know what the x is. So, but I want to make sure that it's represented because it can now go into itself as well. Seems a little tricky, but that's pretty much how we do it. It's not really tricky at all. Here's what it's like. When we've added 1/2 plus 1/3, they don't have anything in common. So my common denominator, you would automatically say 6, but where does that 6 come from? It's because we're multiplying 2 times 3. That's why my common denominator for these is actually 6, and not something else. We want to make sure both numbers or terms are represented. Alright, let's do a little bit of math with these now, if you don't mind, and even if you do, we're still going to do it, and you're still going to take notes, like it or not. So, I'm going to set up my blank fraction, and I'm looking for my LCD. Well, let's look at the numbers first. I have a 7 for this one, and it's the only one with the number, so I want to make sure that that 7 is represented. So they both have to have a 7. Now I'm looking at my variables. I have n cubed, and I have n squared. Similar to what we did for letter A in number 2, I know I need some n's, and I know that I always need the biggest exponent because it can fit into itself, and this one I can just make bigger in order to fit into it as well. Okay, so is it legal to just change the denominators? Heck no, tech no. We changed some stuff. What do we do to go from n cubed to 7n cubed? If you responded out loud, I absolutely positively love you to death. But we added a 7. We multiplied this by 7 actually, and so whatever I multiply the bottom by, I need to now multiply the top by. And then you could pretend like I am a genius, and then I can multiply 7 times 27 in my head, and I'm going to go with that. It's 189. Unless somebody tells me that I messed up later on. But I did catch this, and I bet you probably did too. This is subtraction, not addition. I wonder how many people already stopped the video and talked to me about it. Sit back down. I got it. I fixed it. I also changed this one though. The 7 was here. 7's here. Checked. But I went from n squared to n cubed. What do I need to multiply n squared by to become n cubed? I added another n. And so if I did it on the bottom, I'm going to do it on the top as well. Now, 7n squared times n squared times n is n cubed. That means that's just my way of checking myself. Up top, I have 9n. Beautiful. Now I have my common denominator, 7n cubed. I can now combine the numerators, which is 189 minus 9n. Can I add these terms? Heck no. Why? One has an n, one does not. But the question is, can I simplify it? I think so, because I believe that 9 can go into both of these terms. So I'm good with the 7n cubed. But in my mind, I know that 9 can also go in here. 3 goes into both of these terms, absolutely. 1 goes into both of these terms, absolutely. But the biggest number that I can see that I can divide both of these by is 9. I'm dividing by 9 to factor out that 9. And 9 goes into there 21 times. Minus, and then 9 goes into here, n. So if I were to multiply this back out, I would get right back to this problem right here. We want to leave everything in factored form. Why, you may ask? Well, because just like when we have to reduce our answers at times, like we did for number 2 on the warm-up, sometimes it ends up working out so where we can reduce these fractions as well. We want to write our answers in the most simplest form possible. The most simplest form possible. All right, let's try another one just like the other one. Find the sum or difference for letter B. There it is. There it is. Got him. First thing I need to do, what? Find a common denominator. Notice how big I'm writing my fraction bar? I'm thinking ahead, guys. I'm thinking ahead. I'm looking at these two fractions, 1 over g plus 2 times 1 over g plus 1, and I'm realizing they don't really have anything in common. I know what you're thinking. They both have a g, misfits. No one cares because this is g plus 2, this is g plus 1. Two completely different numbers. So, since they don't have anything in common, they are relatively prime. Little vocab for you. So I'm just going to write them side by side. Nothing I can do. Beautiful. Now what? Well, again, we can't just alakazam, lost my lighting. We can't just alakazam and change it. We have to do this legally. So whatever I multiplied by this one, so this g plus 2 was already here. I added a g plus 1 on the bottom, so I'm going to multiply a g plus 1 on the top as well. Well, now I'll distribute. 1 times g is g. 1 times 1 is 1. Similarly, I added a g plus 2, and now I'm going to distribute. What's 3 times g? 3g. What's 3 times 2? 6. Beautiful. My common denominator stays. And then g plus 3g is 4g. 4G networks. 1 plus 6 is 7. Can I factor that? Absolutely not. So that's my final answer for that. I like it. I hope you like it as well. I'm not sweating. I don't know. I just spilled. Here we are. So here's what I want to challenge you to do, encourage you to do. Press pause right now if you are feeling pretty good about this, and then see how you do. Okay, so for those of you that did not want to press pause and you kind of just want to roll with me here, that's cool. If you did press pause, go ahead and kind of like watch me at ×2, ×4 speed or something so you're not bored. So making a big fraction, I'm looking at x minus 5 and x plus 4. Nothing in common because minus 5 and plus 4 not getting me the same number. So I'm going to write these side by side, which is actually kind of low-key nice that we can do that. Now, what did you do to change that? Well, for this one, I'm adding an x plus 4 top and bottom. And let's distribute. 2x times x is 2x squared. 2x times 4 is 8x. And then for this one, I went from x plus 4 and I added an x minus 5. And I get distributing 9 times x, 9x. 9 times negative 5, negative 45. Bueno, let's keep going. Keep it pushing. Denominator is great, just the way that it is. Numerator, combining like terms. Well, what are they? Well, I have 2x squared as my biggest exponent, nothing alike with it. But I have 8x plus 9x. 8x plus 9x is 17x. And then minus 45. That is a delight. I wonder if this is factorable. I don't know. We can try, right? How do we factor these? Well, we'll take the first and last term. I need two numbers that will multiply to give me negative 90x squared. And that will add to give me 17x. Well, guess what? Those two numbers do not exist. There aren't two numbers. There's like 2 times 45, there's 9 times 10, whatever combination we come up with, none of them are going to do that. So this is not factorable. It would have been really cool if I could have factored it and then I could have done a little bit more reducing like we did for number 1b, also known as 1a, but we can't. So I was thinking, yay, a box. That'd be cool. I love the box. No, didn't work out for me. So this is my final answer. Thank you for joining me. Hope that you have a wonderful, delightful day.